Welcome to the Basic Data Center Architectures and Deployment Scenarios module. By the end of this module, you should be able to describe the basic architectures and deployment scenarios used for data centers.
Planning is key to implementing successful data center environments. The initial design should take into account several factors, including VLANs. How many VLANs will be required within the domain? How will traffic flow within the same VLAN? How will traffic flow between hosts in different VLANs? Reachability. Do applications require Layer 2 communication? Do applications require Layer 3 communication? What external networks, internet, corporate, WAN, and so on, will applications be required to communicate with? Security. What traffic will be required to pass through a security domain? How will that security domain be implemented? Is an edge firewall sufficient and scalable? Will a security domain that contains several security devices be required? Scalability. How will the initial design be impacted when the data center scales?
In the example design, you use the given parameters, the spine and leaf topology, virtual extensible LAN or VXLAN with Ethernet VPN or EVPN control plane for Layer 2 domains, Layer 2 gateways implemented at the leaf nodes, Layer 3 gateways implemented at the spine nodes, centrally routed bridging or CRB design, and a security domain through which traffic to external destinations must pass. This example is a simple spine leaf topology. You can increase the number of spine and leaf devices as needed without impacting the design. You can dual home servers to leaf devices, which requires 2 leaf devices per rack of servers. A single internet gateway is implemented. Alternatively, you may choose to deploy a dual gateway. If you deploy a dual internet gateway, it is recommended to have a chassis cluster with a link aggregation group or lag to the spine devices. On the spine devices, you can implement an EVPN lag interface, assigning the security chassis cluster to the same Ethernet segment identifier or ESI. You can achieve access outside the fabric through border leaf devices or service leaf devices.
Multiple options are available for the underlay network. A simple interior gateway protocol or IGP underlay is usually sufficient for a basic IP fabric data center design. The goal of the IGP is to advertise loopback addresses to all other fabric devices, which enables the ability to use loopback addresses for the overlay BGP peering sessions.
The overlay for the data center is based on multi-protocol BGP, internal BGP or IBGP or external BGP or eBGP. The Juniper Apstra software product only supports eBGP. If you use IBGP, you may use a full mesh of IBGP peers or route reflectors to distribute EVPN route information. The IBGP sessions support the family EVPN signaling option. All fabric devices are configured with the same autonomous system number or AS number. It is strongly recommended for the usage of an overlay using eBGP for scalability. When using eBGP for the overlay network, you use loopback addresses for each leaf device to peer with each spine device. The spine devices distribute EVPN route information, and the sessions support the family EVPN signaling option. You configure all fabric devices with different AS numbers. The Ethernet VPN Virtual Extensible LAN or EVPN-VXLAN topology is designed as a CRB design. The leaf devices operate as Layer 2 gateways only. The spine nodes are configured as Layer 2 gateways, which are virtual tunnel endpoints or VTEPs, and as distributed Layer 3 gateways that use integrated routing and bridging or IRB interfaces within the Layer 2 domains. The resulting topology creates a full mesh of VXLAN tunnels within the data center.
Layer 2 traffic between hosts that are connected to different VTEPs traverses VXLAN tunnels between the Layer 2 gateways.
Be forwarded between VLANs is forwarded to the spine devices. The spine devices route the traffic to the new virtual network identifier or VNI and forward it to the destination VTEP in the destination VNI. The remote VTEPs de-encapsulate the traffic and forward it to the host. Traffic destined to external destinations is forwarded to the spine devices. You configure the IRB interface on the spine device as the default gateway for all VNIs within the VXLAN. Once the traffic arrives on the spine device, it routes to the destination VNI, which is the VLAN associated with the link that connects to the external security device. The traffic is then forwarded to the external security device, which performs network address translation or NAT and other services prior to passing traffic to the external destination. External traffic arrives on the external security gateway, is processed, and then is forwarded to the VXLAN Layer 3 gateway. The VXLAN Layer 3 gateway forwards the traffic to the VXLAN VNI that corresponds to the destination host. Layer 2 gateway functions are performed on each leaf device. The VXLAN environment requires EVPN signaling to all fabric devices. If you choose to use IBGP peering, ensure you create a full mesh of all spine and leaf devices within the fabric. Alternatively, you can peer leaf devices to a centralized set of route reflectors. The centralized route reflectors design is more scalable because as new leaf devices are added, only peer sessions from the new leaf to the route reflectors are required. The alternative of a full mesh topology requires that every leaf node in the network creates an IBGP session with the newly added leaf. Providing EVPN signaling through eBGP provides higher scalability than IBGP with all the same benefits. Each fabric device has a unique autonomous system number. Each spine device peers with every leaf device through loopback interfaces. As new leaf devices are added, the spine devices automatically update the existing leaf devices since each leaf only peers with spine devices. It is strongly recommended to use eBGP as your overlay solution. The Juniper Apstra software only supports IBGP in the overlay when using freeform. Layer 3 gateways are on the spine devices and therefore the Layer 3 routing functions do not change as more leaf devices are added. The only exception is when new spine devices are added in the future. One downside to this topology is that it requires all inter-VLAN traffic within the data center to pass through the spine nodes. As new leaf devices are added, the BGP signaling automatically advertises the new leaf and new VTEP to the devices within the VXLAN, and new VXLAN tunnels are automatically created.
With this design, all inter-VLAN traffic must pass through the Layer 3 gateway at the spine nodes. This is known as hairpinning in the network. A downside to hairpinning is that it utilizes uplink and downlink bandwidth and adds unnecessary hops to traffic that is forwarded between devices that are connected to the same VTEP. Another downside to this topology is that the failure of a gateway device may have a more severe impact on traffic within the data center. Not only does all Layer 2 traffic exiting the domain have to pass through a single spine device, but also all Layer 3 traffic processing for inter-VLAN routing must be processed by the remaining spine device and its fabric links.